Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring the fascinating story of ancient astronomy and discovering the remarkable ways our ancestors tried to understand the universe. Long before modern science had a name, people were already asking serious questions about the heavens. They noticed that certain movements returned with surprising precision. And over generations, those observations became systems of knowledge that could shape entire societies. Ancient astronomy reveals the true ingenuity of humanity, even in times without advanced technology. With patience alone, early astronomers measured cycles that stretched far beyond a human lifetime. Their records preserved events that modern researchers can still study today. Some of their conclusions were remarkably accurate. Others were shaped by ideas that later science would overturn. But all of them mattered, because every attempt brought humanity closer to seeing the universe as a place governed by patterns we can understand. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is get settled in. Let your shoulders soften, let your breathing slow, and allow your mind to settle into stillness as we embark on this fascinating journey through the ancient sky together. Let's begin. Ancient astronomers predicted eclipses long before telescopes existed. In the ancient world, patient observers learned that these events followed patterns. They did not need glass lenses or space probes. They needed memory, mathematics, and generations of records. Babylonian scholars were especially skilled at this. By watching the moon over centuries, they noticed that eclipses often returned in a repeating cycle, now called the Saros. It lasts a little more than 18 years. After one cycle, the sun, earth, and moon come close to lining up in a similar way again. This did not make every eclipse easy to predict for every location, but it gave ancient astronomers a powerful warning system. Imagine living in a world where the sun suddenly dimmed, and yet someone had already expected it. That ability must have seemed almost impossible. It shows that astronomy began not with machines, but with careful eyes and inherited knowledge. The night sky was humanity's first clock, map, and calendar. Before written schedules, mechanical clocks, or printed maps, the sky gave people a dependable way to organize life. The rising sun divided day from night. The moon offered a visible rhythm that changed across a month. The stars returned in familiar patterns as the seasons turned. For early communities, this was not a distant hobby. It affected survival. A bright star appearing before sunrise could signal that rains were coming. A certain constellation in the evening could tell hunters or farmers that a familiar season had arrived. Travelers used the sky to hold direction when landscapes became confusing. The heavens became a shared system that every generation could learn. It was above every village, every field, and every shoreline. What makes this so remarkable is that the sky was both beautiful and practical. It helped people plant food, hold ceremonies, measure time, and move through the world. Long before astronomy became a science, it was already part of everyday life. The Great Pyramid aligns with the cardinal directions astonishingly well. The Great Pyramid of Giza is not only famous for its size, it is also remarkable for its orientation. Its sides are aligned very closely with north, south, east, and west. The builders achieved this more than 4,000 years ago, without compasses, satellites, or modern surveying instruments. That precision has fascinated researchers for generations. One likely method involved watching stars near the northern sky, especially stars that circled around the pole and never set below the horizon. By observing pairs of these stars as they moved, ancient Egyptian surveyors may have found true north with impressive accuracy. Another possibility involves careful solar shadow measurements. However they did it, the achievement shows that monument building and astronomy were deeply connected. The pyramid was not placed casually in the desert. It was fixed into the order of the heavens. Stone, geometry, and sky became part of one design. Its alignment reminds us that ancient engineering often began by looking upward. Ancient Chinese astronomers recorded supernova that modern science can still identify. A supernova is one of the most violent events in the universe, but to ancient eyes, it could appear as a strange new star. Chinese astronomers were among the best record keepers of such events. They called these sudden lights guest stars because they arrived in the sky, stayed for a while, and then faded away. Their records often included where the object appeared, how bright it seemed, and how long it remained visible. One famous observation from the year 1054 describes a brilliant guest star in the region we now associate with the Crab Nebula. Today, astronomers know that nebula is the expanding remnant of a stellar explosion. The ancient record helps connect the object we see now with the event that created it. That is astonishing. A court astronomer writing with brush and ink helped modern scientists understand a cosmic blast. Across nearly 1,000 years, one careful note became evidence for the life and death of a star. Greek thinkers realized Earth was round by studying shadows. The idea of a spherical Earth was not guessed from space, of course. It grew from observation. Greek thinkers noticed things that did not fit a flat world. During a lunar eclipse, Earth's shadow on the moon always looked curved. Ships disappearing over the horizon seemed to sink hull first, rather than simply shrinking evenly into distance. Different stars appeared as travelers moved north or south. These clues pointed toward a globe. Aristotle argued for the roundness of Earth using several of these observations. Later, others refined the idea with measurement and geometry. The brilliance of this discovery is that it came from ordinary phenomena, carefully interpreted. A shadow on the moon became a clue about the shape of the world. A ship on the sea became evidence for curvature. This was one of the great leaps in human thought. People realized that the ground beneath them was not an endless plain. It was part of the vast sphere suspended beneath the sky. Polynesian navigators crossed oceans by reading stars without instruments. Across the Pacific, skilled navigators made voyages that still inspire awe. They crossed enormous distances in canoes, often without written charts or metal tools. Their knowledge lived in memory, training, and practice. Stars were central to this art. A navigator knew where important stars rose and set on the horizon. Each star could act like a direction marker. As the night changed, one guide would descend and another would take its place. But stars were only part of the method. Navigators also read ocean swell, wind, bird flight, cloud shape, and the behavior of light near islands. The sky worked together with the sea. This knowledge was not vague instinct. It was a disciplined system passed from teacher to student. To sail this way required concentration beyond anything most of us can imagine. The navigator became a living instrument, holding an entire ocean in the mind. Ancient astronomy was not always written in observatories. Sometimes it traveled across water under a moving canopy of stars. Stonehenge may have helped mark solstices thousands of years ago. On Salisbury Plain in England, Stonehenge still stands with a presence that feels deeply intentional. Its great stones were arranged long before modern astronomy, yet the monument connects powerfully with the sun's yearly cycle. At the summer solstice, the sun rises near the direction of the heel stone when viewed from the center of the monument. At the winter solstice, attention may have focused on the opposite direction, when the sun sets at its lowest yearly point. Archaeologists debate exactly how the site was used, but the solar connection is hard to ignore. For ancient communities, the solstices mattered. They marked extremes in light, turning points in the year, and moments when seasonal expectation could become ceremony. Building such a monument required labor, planning, and shared purpose. Its stones were not simply lifted for decoration. They shaped experience. People could gather and watch the year turn in the architecture itself. Stonehenge reminds us that ancient astronomy was often public, physical, and deeply communal. Ancient astronomy turned the sky into a guide for civilization itself. When people learned to read the heavens, they gained more than knowledge of distant lights. They gained a framework for organizing society. The sky helped rulers choose ceremonial dates. It helped farmers prepare for seasonal change. It gave priests a structure for ritual life. It gave travelers confidence in unfamiliar places. Because celestial patterns seemed stable, they offered a sense of order in a world filled with uncertainty. This made astronomy useful to cities, temples, courts, and farming villages alike. It also encouraged record-keeping. Once people believed the sky mattered, they had reason to watch it again and again. Over time, those observations became calendars, predictions, myths, mathematical tables, and monuments. The study of the heavens became one of the foundations of organized culture. It linked practical needs with deeper questions. What is time? Where are we? What power governs change? Ancient astronomy did not merely explain the sky. It helped humans build meaning, authority, and rhythm into life on Earth. Babylonian astronomers divided the sky into zodiac constellations. The zodiac began as a practical way to follow the paths of the sun, moon, and planets. Babylonian astronomers focused on the band of sky, where these bodies appeared to travel. They divided that region into recognizable sections associated with constellations. Over time, these divisions became a powerful reference system. A planet could be described by its position within a certain part of the zodiac. This made records clearer and predictions more systematic. The familiar names later passed through Greek astronomy and eventually into wider tradition. Today, many people know the zodiac mainly through astrology, but its roots include serious sky measurement. It was a coordinate system before it became a cultural symbol. The Babylonians needed a way to describe a moving heavens with accuracy. By giving structure to the apparent road of the planets, they created a lasting map of celestial motion. Every horoscope column is a faint echo of an ancient effort to bring order to the wandering lights. Egyptian priests used Sirius to anticipate the Nile flood. In ancient Egypt, the annual flooding of the Nile was a matter of life and death. It brought water and fertile silt to the fields. Without it, crops could fail. One celestial event became especially important. The star Sirius returned to visibility just before sunrise, after being hidden in the sun's glare. This heliacal rising happened close to the season when the Nile flood began near Memphis in earlier periods. Egyptian priests watched for it with great attention. The star's return became associated with renewal, abundance, and the start of the year. This connection between sky and river helped shape one of the world's great agricultural civilizations. The wonder lies in how a star and a flood became linked in human understanding. A bright point above the horizon could announce a transformation on Earth. It was not magic in the modern sense. It was pattern recognition across time. The Egyptians learned that the heavens could help them prepare for the river's gift. The Antikythera mechanism modeled celestial cycles with bronze gears. This object was found in a shipwreck near the Greek island of Antikythera. and it changed how scholars imagined ancient technology. At first, it looked like corroded fragments of metal. Later study revealed something extraordinary. Inside were gears, inscriptions, and mechanical relationships designed to calculate astronomical cycles. The device could show positions of the sun and moon. It could predict eclipse seasons. It also included calendar functions connected to Greek timekeeping. Nothing else from the ancient world has survived quite like it. Its craftsmanship suggests a tradition of precision engineering that must have been more advanced than the surviving evidence once implied. Imagine turning a handle and seeing celestial rhythms expressed through interlocking teeth of bronze. The sky was being translated into machinery. This was not a telescope, and it did not magnify anything. Instead, it made time itself mechanical. The mechanism proves that ancient astronomy was not limited to observation. It could also become an intricate model you could hold in your hands. Hipparchus discovered Earth's slow wobble by comparing star positions. Hipparchus was one of the great astronomers of the ancient Greek world. His achievement came from noticing that the heavens were not quite as fixed as they seemed. By comparing his own observations with earlier records, he found that the positions of stars had shifted slightly relative to the equinoxes. This led him to identify what we now call precession. Earth's axis slowly wobbles, like a spinning top moving under a gentle pull. The effect is extremely slow, taking about 26,000 years to complete one full cycle. No single lifetime could watch it unfold directly. That is what makes the discovery so impressive. Hipparchus found a vast motion by comparing careful measurements across time. The stars looked eternal and unchanging to the naked eye, yet hidden beneath that stillness was a grand celestial drift. His insight showed that astronomy could reveal movements too slow for ordinary perception. It expanded the scale of time that humans could meaningfully understand. Eratosthenes measured Earth's size using sunlight and simple geometry. Eratosthenes worked in Alexandria, a center of learning where reports from distant places could become scientific evidence. He heard that in Sin, near modern Aswan, the sun shone straight down a well at noon on the summer solstice. At the same moment in Alexandria, a vertical stick cast a shadow. That difference mattered. If Earth were flat, the sunlight should have fallen at the same angle in both places. Instead, the shadow revealed curvature. Eratosthenes measured the angle, estimated the distance between the two cities, and used geometry to calculate the circumference of Earth. His result was astonishingly close, depending on the exact length of the unit he used. The beauty of this experiment is its simplicity. A stick, a shadow, and a careful question were enough to measure a planet. No ocean voyage was needed. No spacecraft looked back from orbit. By trusting reason and observation, Eratosthenes turned sunlight into a measuring tape wrapped around the world. Chinese observers kept some of history's longest sky records. For many dynasties in China, the heavens were considered closely connected to the state. Because of that belief, official astronomers were appointed to watch the sky and record unusual events. Their work produced an extraordinary archive. Over centuries, they noted eclipses, comets, guest stars, planetary conjunctions, meteors, and other phenomena. These records were often dated carefully because they mattered politically and ritually. Today, historians and astronomers value them for a different reason. They provide a long timeline of real sky events seen before photography or telescopes. Some entries help identify supernova remnants. Others help track the history of comets or refine ancient eclipse calculations. The power of the archive comes from continuity. Many cultures watched the sky, but few maintained official records across such long stretches of time. Each note may seem small by itself, Together, they form a bridge between ancient court life and modern astrophysics. The sky changed, and someone was there to write it down. The Maya Dresden Codex includes detailed tables for eclipse prediction. The Dresden Codex is one of the most precious surviving books from the ancient Maya world. Its pages carry astronomical tables that reveal an advanced understanding of repeating sky patterns. Among its most intriguing sections are eclipse tables. These did not predict eclipses in the modern local sense with exact maps and times. Instead, they identified intervals when eclipses were likely because the sun and moon returned near the right alignment. The tables show how carefully Maya specialists watched lunar cycles and incorporated them into their calendar system. They used arithmetic to track danger periods across long spans. In a culture where celestial events carried ritual significance, knowing when such events might occur was powerful knowledge. What is so striking is that this information survived in a folded bark paper manuscript. Many Maya books were destroyed after the Spanish conquest, so the Codex is a rare window into a much larger intellectual tradition. Its pages preserve the science of cycles, memory, and prediction. Ancient Mesopotamians treated unusual sky events as royal warnings. In Mesopotamia, the heavens were read as messages from the gods. This belief gave unusual celestial events enormous importance. A lunar eclipse, strange halo, bright comet, or unusual planetary arrangement could be interpreted as a warning about the king, the land, or the future of the state. Scholars gathered these interpretations into omen texts. One of the most famous collections is known as Enuma Anu Enlil. It connected specific sky appearances with possible earthly outcomes. To modern ears, this sounds far from science. Yet the system required detailed observation, careful classification, and extensive written tradition. When the court wanted guidance, scholars needed records. Their religious worldview pushed them to become disciplined watchers of nature. Sometimes rituals were performed to reduce danger. In extreme cases, a substitute king could briefly take the throne during an ominous period. The practice reveals a world where astronomy, politics, and fear were deeply connected. The sky was not distant. It was part of government. Greek astronomers knew planets wandered differently from fixed stars. To ancient observers, most stars kept their patterns. They rose and set together, holding the same shapes night after night. A few lights behaved differently. These were the planets, whose name comes from a Greek word meaning wanderers. They moved against the background stars, sometimes slowing, brightening, or reversing direction for a time. This strange backward motion was especially challenging. Mars made it obvious, but Jupiter and Saturn did it too. The Greeks recognized that these objects needed special explanation. They were not simply stars with unusual brightness. They followed paths that demanded geometry. This problem became one of the great engines of ancient astronomy. How could a universe built on order produce such loops? Different thinkers offered different models, and each tried to preserve regularity beneath apparent confusion. The wandering planets taught astronomers that the sky was not just a dome of fixed lights. It contained bodies with individual behavior. Their puzzling paths forced mathematics to reach upward. Ptolemy's geocentric model guided astronomy for more than 1,000 years. Claudius Ptolemy lived in Roman Egypt, and his great astronomical work became one of the most influential books in scientific history. He placed Earth at the center of the cosmos, as most scholars of his era expected. Around it, he built a mathematical system that described the motions of the sun, moon, and planets. The model used circles upon circles, including devices called epicycles, to account for planetary loops and changing speeds. Its purpose was not simply philosophical. It could generate predictions. For centuries, astronomers in the Islamic world and medieval Europe studied, commented on, improved, and taught his system. Even when later thinkers challenged it, they had to understand it first. Its long success came from its practical power and mathematical detail. Ptolemy's universe was wrong in its central claim, but it was not foolish. It was a serious attempt to save the appearances of the sky. Its endurance shows how powerful a useful model can be, even before the deeper truth is known. Indian astronomers developed sophisticated methods for tracking planetary motion. Across ancient India, astronomy grew into a precise mathematical tradition. Scholars were not only watching the heavens, they were building calculation systems that could describe where planets should appear against the stars. Texts known as Siddhantas set out rules for predicting celestial positions, using cycles, angles, and numerical procedures. These methods helped astronomers prepare calendars and choose ritual timings, but they also show a deeper scientific curiosity. Planets do not move evenly across the sky from Earth's point of view. They speed up, slow down, and sometimes appear to reverse. Indian astronomers created models to handle those changes with impressive skill. Later figures such as Aryabhata described Earth's rotation as a way to explain the daily rising and setting of the heavens. That idea was bold in a world where most people felt the ground was still. Ancient Indian astronomy reminds us that the history of sky science was not confined to one region. Many cultures were solving the universe in their own mathematical language. The Nebra sky disk may show Europe's oldest known star map. Found in Germany and made from bronze with gold symbols, this remarkable object looks simple at first. A bright round disk, a crescent, and scattered dots appear across its dark surface. Yet those shapes may represent the sun, the moon, and a cluster of stars often identified as the Pleiades. It is more than 3,000 years old, which makes it one of the most extraordinary sky-related artifacts from Bronze Age Europe. Some researchers believe it may have helped reconcile lunar and solar calendars. In other words, it may have guided people through the problem of keeping moon months aligned with the farming year. Later additions to the disk appear to mark horizon arcs, possibly connected with where the sun rose and set at different times of year. Whether it was a scientific tool, a sacred object, or both, it reveals a society thinking carefully about the sky. The disk feels like astronomy held in the palm of a hand. Egyptian temples were often aligned with sunrise on sacred dates. In ancient Egypt, a temple was not only a building, it was a carefully placed meeting point between the human world and divine order. Many temples were oriented so that sunlight entered in meaningful ways at particular times of year. A ray at dawn could travel through a doorway, cross a hall, and illuminate a sacred space. This effect was not accidental. It required planning, observation, and architectural precision. The date might relate to a festival, a royal celebration, or the worship of a particular deity. When the sun appeared in exactly the expected place, it confirmed that the temple stood within a cosmic pattern. To witness such a moment must have been powerful. The stone itself seemed to awaken. Modern visitors may admire columns and carvings, but the original experience also involved timing. The structure was designed to work with the sky. Egyptian sacred architecture turned sunrise into a recurring event of meaning. Babylonian clay tablets preserved centuries of planetary observations. Clay may seem fragile, but when baked by sun, fire, or accident, it can outlast empires. That is why so much Babylonian astronomy survived. Scribes pressed wedge-shaped marks into tablets, recording dates, positions, appearances, and celestial patterns. These documents were not casual notes. Many belong to organized traditions of observation and calculation. Over generations, the records grew into a vast archive of sky behavior. A planet's position on one night might mean little by itself, but thousands of such entries could reveal patterns too slow for one person to understand. The tablets also show how astronomy depended on institutions. Temples, courts, scribes, and scholars all helped preserve the work. When modern historians read these marks, they are not just reading ancient language. They are hearing the rhythm of repeated watching. A hand pressed wet clay after a night under the stars, and that small act carried planetary knowledge across more than 2,000 years. Ancient sailors used Polaris before compasses reached common use. At sea, the horizon can erase almost every landmark. This made the northern sky especially valuable. Polaris sits close to the North Celestial Pole, so it appears nearly fixed, while other stars circle around it. For sailors in the northern hemisphere, its position offered a dependable guide. By finding it, they could estimate north and keep a course through darkness. Its height above the horizon also gave a rough sense of latitude. The higher it appeared, the farther north a traveler had gone. This was not modern navigation with charts and instruments, but it was powerful enough to support long voyages. The star did not always hold the exact role it has today, because Earth's axis slowly changes its pointing over very long periods. Yet in many historic eras, it was close enough to serve as a celestial anchor. Imagine steering a vessel through black water while one steady point watched overhead. That single light could mean direction, safety, and home. The Dogon people preserved careful traditions about seasonal sky patterns. In Mali, Dogon communities developed rich traditions connected with the heavens. Their sky knowledge has often been discussed in exaggerated or distorted ways, so the real story is worth treating with care. Like many agricultural societies, the Dogon paid attention to seasonal patterns because timing mattered. Stars, rains, planting, and ceremony belonged to a connected cycle of life. Certain appearances in the sky could help mark when activities should begin. Oral traditions preserved this knowledge across generations, not in textbooks, but through teaching, ritual, story, and observation. That makes it different from court astronomy written on tablets, but not less meaningful. It shows another way humans can maintain an understanding of the sky. Knowledge can live in memory when a community values it deeply enough. The Dogon example invites us to remember that ancient astronomy was not always separated from culture. It often belonged inside daily life, where the sky helped people understand time, land, and responsibility. Chinese astronomers described sunspots long before telescopes revealed them. The sun seems smooth to the naked eye most of the time. Yet under certain conditions, especially when haze, dust, or thin cloud reduces its glare, dark marks can be seen on its face. Chinese astronomers recorded such features centuries before telescopes made them easy to study. Their reports described spots appearing on the sun, sometimes comparing them to birds, eggs, or other visible shapes. These observations were carefully noted because unusual solar appearances mattered to imperial skywatchers. Today, we understand sunspots as cooler regions caused by intense magnetic activity. They come and go as part of the sun's changing behavior. Ancient observers did not know the physics, but their records still matter. They provide evidence that solar activity was noticed and remembered long before modern instruments. It is astonishing to think of someone looking through a veiled sky, seeing a dark mark on the brilliant sun, and deciding it was important enough to write down. The moon helped ancient cultures divide time into months. The moon offers one of the clearest cycles in nature. It grows from a thin crescent, becomes full, fades again, and disappears into darkness before returning. This rhythm is easy to see. and it repeats often enough to organize human activity. Many ancient calendars began with lunar months because the moon gave time a visible shape. People could look up and know roughly where they were within the cycle. This mattered for religious observances, travel, fishing, agriculture, and social gatherings. A moon-based month was not perfectly matched to the solar year, which created challenges later. Still, its appeal was obvious. The moon was a clock everyone could share. It did not require a palace, a priesthood, or a measuring tool. Its changing face moved above rich and poor alike. When ancient people counted nights by the moon, they were turning the sky into a public calendar. Time itself became something bright enough to watch. Greek philosophers debated whether the stars were distant suns. To many ancient people, stars were lights fixed to the heavens. Yet some Greek thinkers wondered whether they might be far more like the sun than they appeared. This was a startling idea. The sun dominates our sky with heat and brilliance, while stars look like tiny points. To suggest a connection required imagination and reasoning. If stars were suns, then their faintness might come from incredible distance rather than weakness. This thought opened a door toward a much larger universe. Not every philosopher accepted it, and ancient cosmology still kept many mistaken assumptions. Even so, the question itself was profound. It challenged the comforting idea that the cosmos was small and centered around human experience. A star might not be a decoration on a heavenly shell. It might be a blazing body in its own right. That possibility made the night sky deeper. It turned each point of light into a question about distance, scale, and reality. Ancient eclipse records help modern scientists study Earth's rotation. When ancient observers wrote down eclipses, they were recording more than dramatic sky events. They were also leaving clues about the motion of Earth. Today, scientists can calculate when past eclipses should have occurred. They can compare those calculations with old reports from places such as China, Babylon, and the Mediterranean world. If the timing or path does not match perfectly, the difference can reveal how Earth's rotation has changed over time. Our planet is not a flawless clock. Tidal friction, interactions with the moon, and shifts within Earth gradually alter its spin. These changes are tiny across a human lifetime, but they become measurable across centuries. Ancient records therefore help connect human history with planetary physics. A scribe who noted darkness at an unexpected hour could not know that future scientists would use the report this way. Yet the observation became part of a grand measurement. The turning Earth left evidence in the written memory of its people. The Inca watched horizon towers to track the sun's yearly path. Near Cusco, the Inca created a system that used the horizon as a solar measuring line. Towers placed along a ridge marked where the sun rose or set at different times of year. From certain viewing points, observers could watch the sun move gradually along the horizon as seasons changed. This was a practical and ceremonial achievement. In a mountain landscape, the horizon is not a flat line. It is jagged, specific, and memorable. By using it carefully, the Inca could track agricultural timing and ritual moments. The system linked astronomy with state organization because controlling calendars meant helping coordinate labor, festivals, and offerings. It also shows how observatories do not always need domes or lenses. A well-chosen viewing place and a marked skyline can become a precise instrument. The sun's motion was not measured in isolation. It was tied to land, power, and seasonal responsibility. The horizon became a calendar written across the mountains. Chaco Canyon buildings align with solstices and lunar standstills. In the American Southwest, Chaco Canyon contains monumental structures that reveal careful attention to the sky. Some buildings and features appear connected with the rising or setting points of the sun at solstices. Others may relate to lunar standstills, which are longer cycles in the moon's rising and setting extremes. These alignments are not simple to interpret, and archaeologists continue to debate their meanings. Still, the evidence suggests that sky watching shaped the experience of the landscape. Jako was not merely a settlement. It was a center of ceremony, gathering, and regional connection. Astronomy may have helped give structure to these activities. One famous site, often called the Sun Dagger, used rock slabs and light patterns to mark solar events before it was disturbed by erosion and visitation. What makes Jako so compelling is the blending of architecture and horizon. Walls, roads, and natural features all seemed to belong to a wider order. The canyon itself became part of the sky's calendar. Ancient Koreans built observatories to monitor the heavens. In the kingdom of Silla, a stone tower known as Cheomseongdi was built at Gyeongju. It is often described as one of the oldest surviving astronomical observatories in East Asia. Its exact use is still discussed, but its association with sky monitoring is deeply important. The structure reflects a society that valued celestial knowledge enough to give it a permanent architectural form. Korean astronomers recorded eclipses, comets, meteors, and other events across different historical periods. As in neighboring cultures, the heavens were connected with the health of the realm and the responsibilities of rulers. Watching the sky was therefore both scientific and political. Cheonseongdi's simple shape can be deceptive. It represents an organized effort to observe, record, and interpret the heavens. A person standing there was not merely looking upward for beauty. They were participating in a state tradition of cosmic attention. The tower reminds us that ancient astronomy had many centers, and Korea was one of them. The Babylonians recognized repeating eclipse patterns across many generations. An eclipse is too rare for one lifetime to reveal all its secrets easily. The Babylonians overcame this by preserving observations across generations. They learned that eclipses belonged to repeating families, connected by the rhythms of the moon's orbit. Their records allowed scholars to identify periods when an eclipse was more likely. This was especially valuable for lunar eclipses, which are visible over large parts of Earth when they occur. The achievement did not come from a sudden revelation. It came from disciplined continuity. One observer wrote what he saw. Another inherited the record. A later scholar compared patterns and improved the expectation. Over time, the sky became less unpredictable. This was mathematics born from patience. It also shows how science can be collective across centuries. No single Babylonian had to understand the whole pattern alone. The culture created a memory large enough to notice what individuals could not. The moon's shadow became a lesson in the power of long attention. Egyptian star clocks helped measure nighttime hours before mechanical clocks. In ancient Egypt, the night was not simply darkness between 2 days. It could be divided and measured by the stars. Egyptian star clocks used groups of stars known as decans, which rose in sequence through the night during particular parts of the year. By watching which star group appeared at a certain time, observers could estimate the passing hours. This was important for temple rituals, funerary beliefs, and organized labor. The system changed with the seasons, so it required trained knowledge. Later, coffin lids and tomb ceilings preserved diagrams showing star arrangements and timekeeping ideas. These were not clocks in the modern mechanical sense. They were celestial schedules. The sky itself provided the moving parts. Imagine a priest watching the eastern horizon while a specific star rose into view, signaling that another portion of the night had passed. Long before gears ticked on walls, time could be read in the slow procession of starlight. Polynesian star paths guided voyages across the Pacific Ocean. A star path is a line of direction remembered through the rising and setting points of stars. In Polynesian navigation, these paths helped sailors maintain a course over immense stretches of open water. A navigator did not follow one star all night. Stars rise, climb, and set, so the course had to be handed from one star to another as the sky turned. This required a mental map of the horizon, sometimes called a star compass. Each star belonged to a directional house. The navigator learned these houses through repetition until the pattern became part of memory. Under clouded skies, the system could be supported by wave patterns and other signs, but the star compass remained central. What is remarkable is how exact this knowledge could be without written charts. The ocean was not empty to trained eyes. It was crossed by invisible roads. The stars did not merely shine above the canoe. They helped draw the route ahead. Ancient Chinese records captured Halley's Comet centuries before its naming. Halley's Comet is famous today because its return can be predicted. But long before Edmund Halley connected its appearances, Chinese astronomers had recorded visits by the same comet across many centuries. They described bright-tailed objects moving through the sky, often noting their positions among star groups and the dates of appearance. These records are precious because comets can be difficult to identify after the fact unless observations are detailed. By comparing ancient descriptions with orbital calculations, modern researchers can link some reports to Halley's Comet. This gives the comet a human history far older than its modern name. In ancient courts, such an object could be alarming. It appeared without warning, grew a tail, crossed the heavens, and vanished. Today, we know it as an icy body returning from the outer solar system on a long path around the sun. The same visitor that startled ancient observers is still part of our sky story. Their records helped give it a past. The Greeks named many constellations still used by astronomers today. Modern astronomy is filled with names inherited from Greek tradition. Orion, Andromeda, Perseus, Cassiopeia, and many others still appear on star charts. These constellations were not invented only as scientific labels. They carried stories, heroes, creatures, and dramatic relationships from myth. Yet their survival in astronomy shows how storytelling and mapping can become linked. A constellation is not a true physical group of nearby stars. Its stars may be at very different distances from Earth. The pattern exists because of our viewpoint. Ancient Greek sky maps turned those patterns into recognizable figures, making the heavens easier to remember and discuss. Later, astronomers adopted and standardized many of these names. This means that when a modern telescope points toward a region of the sky, it may still use a name shaped by ancient imagination. The science has changed completely, but the vocabulary carries memory. The night sky became a library of figures, and some of those figures never left us. Maya cities were sometimes planned around important solar alignments. In parts of the Maya world, architecture could frame the sun with remarkable care. Buildings, plazas, and sightlines were sometimes arranged so that sunrise or sunset appeared in meaningful positions on important dates. These alignments were not only about watching the sky. They helped connect political authority, ritual life, and calendar knowledge. A ruler who could command architecture that worked with the sun seemed linked to cosmic order. At some sites, paired structures allowed observers to mark the sun's movement across the horizon through the year. This may have helped track agricultural seasons and ceremonial timing. The experience would have been dramatic. A crowd could gather as sunlight appeared exactly where tradition expected it. The city itself became a measuring instrument. This kind of planning shows that astronomy did not live only in books or priestly calculations. It could shape streets, platforms, and public space. In Maya urban design, the movement of the sun could be built into stone. The planet Venus shaped calendars, warfare, and ritual timing. In Mesoamerica, Venus carried an intensity that few celestial bodies could match. Its brightness made it impossible to ignore, and its cycle made it useful for timing. Some societies associated particular appearances of Venus with dangerous or powerful moments. The first rising as a morning star could be treated as especially charged. In certain traditions, rulers and priests linked these appearances with warfare, sacrifice, or major ceremonies. This was not random. Venus follows a pattern that can be tracked across years, and that pattern can be fitted into calendar systems. The planet became a schedule for action, as well as a sign in the heavens. What makes this fascinating is the way a distant world affected human decisions on Earth. A point of light near the horizon could influence when armies moved or rituals began. Modern astronomy sees Venus as a planet covered in clouds and heat. Ancient observers saw a brilliant clock with power over human affairs. Ancient astronomers knew the morning star and evening star were Venus. For many observers, it would be natural to assume that the bright light seen before sunrise and the bright light seen after sunset were different objects. They appear at different times and on opposite sides of the day. Yet ancient astronomers eventually understood that they were the same wandering body. This realization required patient tracking. Venus never appears far from the Sun, because its orbit lies inside Earth's orbit. It alternates between evening visibility and morning visibility, disappearing into solar glare between phases. Recognizing the pattern meant seeing through the illusion created by timing. Some ancient cultures gave the two appearances different names, while others connected them. The discovery is powerful because it shows how astronomy corrects first impressions. The sky can present one object as two identities. Only repeated observation reveals the deeper order. Once Venus was understood as a single body moving through a cycle, the heavens became less mysterious in one way and more elegant in another. The sun's solstices marked turning points for farming societies. For communities that depended on crops, the sun's annual movement was not abstract. It shaped the length of days, the warmth of seasons, and the timing of work. The solstices marked the extremes of that movement. One brought the longest day. The other brought the longest night. After each, the balance of light began to change. Farming societies watched these turning points because they helped organize the year. Planting, harvesting, storage, and celebration all depended on seasonal awareness. Solstices also carried emotional force. They showed that darkness would not grow forever, or that the height of light had begun to decline. Many monuments and festivals around the world reflect this deep attention. The sun was both a practical guide and a symbol of renewal. Ancient people did not need modern physics to understand its importance. They felt it in soil, weather, and food. The solstice was the sky announcing that the year had reached a hinge. Lunar eclipses helped ancient thinkers prove Earth casts a round shadow. During a lunar eclipse, the moon passes through Earth's shadow. To ancient observers, this offered a rare chance to see the shape of our planet projected onto another world. The edge of the shadow always appeared curved. No matter when the eclipse happened, the dark bite crossing the moon had a rounded boundary. This was one of the strongest clues that Earth itself was spherical. A flat disk could cast different shapes depending on its angle, but a sphere always casts a round shadow. Greek thinkers used this reasoning with great confidence. The elegance of the argument is hard to overstate. Nobody had to leave Earth. Nobody had to see the planet from outside. The proof arrived in the sky during a temporary darkening of the moon. An event that might have frightened some people became evidence for the shape of the world. The shadow was not only darkness, it was geometry made visible. The Antikythera mechanism could track the 4-year Olympic cycle. Among its astronomical functions, the Antikythera mechanism also included a connection to Greek social time. One dial tracked a 4-year cycle associated with major athletic festivals, including the Olympic Games. This detail is fascinating because it shows that ancient timekeeping did not separate sky cycles from civic life as sharply as we might expect. The same instrument that modeled lunar patterns could also remind users of recurring festivals. To the Greeks, calendars were not merely lists of dates. They structured worship, competition, travel, and identity. A device that coordinated these rhythms would have been valuable in a world of regional calendars and complex timing. The Olympic cycle also had prestige. It helped mark years and connect communities across the Greek world. In this small bronze machine, celestial calculation met public celebration. That combination makes the mechanism feel even more human. It was not built only for abstract astronomy. It linked the movement of the heavens with the rhythms of people gathering on Earth. Babylonian mathematics used base 60, which still shapes timekeeping today. When you count 60 seconds in a minute or 60 minutes in an hour, you are living with an ancient mathematical inheritance. Babylonian scholars worked with a base 60 number system. It may seem unusual to us, but it has real advantages. 60 can be divided evenly by many numbers, including 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. That makes fractions easier to manage in calculation. Babylonian astronomers used this system to describe angles and time with great flexibility. Later traditions inherited parts of it, and it eventually became embedded in how we measure circles and clocks. This is one of those ancient ideas hiding in plain sight. Every time a clock hand moves, it carries a trace of Mesopotamian mathematics. The connection is remarkable because it shows that old astronomy did not vanish. Some of its habits became part of ordinary life. A number system once used for sky calculation now governs the rhythm of our days. Ancient Egyptians linked certain stars with the journey after death. For ancient Egyptians, the night sky was closely tied to beliefs about eternity. Some stars near the northern sky never appeared to set because they circled around the pole. These were sometimes understood as undying stars. Their constant presence made them powerful symbols for the afterlife. Royal funerary texts imagined the dead king joining these imperishable lights, escaping decay and entering a divine realm. Tombs, pyramids, and burial beliefs often reflected this desire for cosmic permanence. The sky was not simply above the dead. It was a destination. This gives Egyptian astronomy a deeply human dimension. Observation of star motion became part of hope, identity, and sacred imagination. The stars that never vanished below the horizon seem to offer a model of survival beyond ordinary life. To watch them circle night after night was to see permanence written in light. In that sense, astronomy helped shape one of Egypt's most enduring questions. How could a human life become eternal? The Pleiades marked planting seasons for cultures around the world. The Pleiades are easy to recognize as a small, shimmering cluster of stars. Because they appear and disappear seasonally, many cultures use them as a sign for practical timing. Their rising or setting at certain times of year could indicate when to plant, harvest, travel, or prepare for seasonal change. This happened in many parts of the world because the cluster is bright, distinctive, and close to the path of the sun. People did not need complex instruments to notice it. They needed clear nights and long memory. In some traditions, the Pleiades also carried stories about sisters, seeds, ancestors, or animals. The beauty of the cluster made it memorable, but its usefulness made it important. It linked the sky directly to food. A farmer looking up before dawn might see those stars and understand that a task on Earth was approaching. The Pleiades remind us that ancient astronomy often began with a simple question: when should we begin? Greek observers estimated the moon's distance using eclipses. Ancient Greek astronomers were fascinated by measurement. They wanted to know not only what the heavenly bodies were, but how far away they might be. Lunar eclipses offered one path toward that question. By studying the size of Earth's shadow as it crossed the moon, thinkers such as Aristarchus developed geometric arguments about the moon's size and distance. The reasoning was difficult, and the results were not always exactly correct by modern standards. Yet the method was extraordinary. It treated the eclipse as a cosmic diagram. Earth, shadow, and moon formed a temporary arrangement that could be measured with thought. The attempt changed the scale of astronomy. The moon was no longer just a shining disk nearby in the heavens. It became a body at a measurable distance, connected to Earth by geometry. This was a profound shift. Ancient observers began turning the sky into a set of proportions, and those proportions made space feel larger than myth alone could hold. Ancient Chinese astronomers worked inside official imperial bureaus. In imperial China, astronomy was a responsibility of government. Specialized officials observed the sky, maintained calendars, and reported unusual events to the court. This work mattered because the emperor's authority was connected with cosmic harmony. If the calendar failed, or if a striking celestial event went unreported, it could be seen as a serious political problem. The bureau system created professional skywatchers whose duties were defined by the state. They used instruments, kept records, and worked within long traditions of observation. This official status helped produce continuity because astronomical knowledge was not left only to private curiosity. It was supported by administration. The result was a rich historical record and a culture where celestial events had formal meaning. Imagine having a job where a comet, eclipse, or planetary conjunction was not only interesting, but urgent news for the throne. Ancient Chinese astronomy shows how the sky could become a matter of governance. Watching the heavens was part of ruling the earth. Mesopotamian priests watched the sky from temple platforms called ziggurats. A ziggurat rose above the flat cityscape like a stepped mountain of brick. These temple platforms were religious centers, but they also offered elevated places where the horizon opened wide. In Mesopotamian cities, priests and scholars connected divine order with celestial signs. Watching from such heights gave them a commanding view of the sky. They could observe the first appearance of a planet, the setting of a bright star, or the glow of the moon above the city. The architecture itself helped create a sense of closeness to the heavens. A ziggurat was not an observatory in the modern sense, yet it belonged to a world where religion and sky watching were deeply joined. The observer stood between earth and heaven, reading signs that might matter to the whole community. This image captures something essential about ancient astronomy. It was not only a technical activity. It was performed from sacred places, under open air, with the fate of cities imagined above. The Maya counted long cycles of time with extraordinary precision. Maya timekeeping was built on the idea that time moved through interlocking cycles. Their long count calendar could place events across vast stretches of history by counting days from a fixed starting point. This gave scribes a way to record dates far beyond ordinary memory. A king's accession, a dedication ceremony, or a mythic event could be located inside a grand structure of time. What makes this so remarkable is the scale. The system was not limited to a farming year or a human lifetime. It could reach backward and forward across thousands of years. Maya inscriptions often tied political events to deep time, making a ruler's actions feel connected to cosmic order. This was mathematics serving memory, power, and belief all at once. Each carved date was more than a timestamp. It was a statement that human life belonged inside a much larger rhythm. The Maya did not merely count days. They built a universe where time itself had architecture. Ancient calendars often blended lunar months with solar years. A lunar month is easy to see, but it does not fit neatly into a solar year. 12 lunar cycles fall short of the time it takes Earth to complete one journey around the Sun. That mismatch created one of the great practical puzzles of ancient timekeeping. If people followed only the moon, seasons would drift through the calendar. A spring festival might slowly slide into winter. Many societies solved this by adding extra months at certain intervals. These are called intercalary months, and they helped keep lunar dates connected to seasonal reality. The challenge was not merely mathematical. It affected farming, taxation, worship, travel, and royal administration. A calendar had to be accepted by a community, or it could not guide shared life. Ancient calendar makers were therefore balancing sky cycles with social needs. The result was a remarkable compromise. The moon gave time its visible rhythm, while the sun kept that rhythm anchored to the year. The Metonic cycle showed how lunar phases repeat across 19 years. The moon's pattern does not match the solar year perfectly, yet there is a striking near agreement. After 19 solar years, the lunar phases return to almost the same dates. This pattern became known as the Metonic cycle in the Greek world. It was not just a clever observation. It offered a way to build calendars that stayed aligned with both the moon and the seasons. By inserting additional months in a planned pattern, calendar makers could prevent drift and keep festivals in their proper part of the year. The beauty of the cycle lies in its usefulness. It turns an awkward mismatch into a manageable rhythm. Ancient people did not need atomic clocks to notice this. They needed records, patience, and a reason to care about recurring dates. The cycle shows how astronomy can become a social tool. A pattern in the sky helped communities agree on time. The moon and the sun, although different in rhythm, could be brought into conversation. Greek astronomers built armillary spheres to model the heavens. An armillary sphere is a framework of rings that represents the great circles of the sky. To an ancient viewer, it made invisible geometry visible. Rings could stand for the celestial equator, the ecliptic, the horizon, and other reference circles. By turning the structure, a teacher could show how stars appeared to move, why the sun's path changed with the seasons, and how celestial coordinates worked. These devices were not toys. They were thinking tools. In a time before planetarium domes and computer simulations, a metal or wooden model could help the mind grasp the order of the heavens. Greek astronomers valued geometry, and the armillary sphere expressed that habit beautifully. It translated the sky into circles you could see from every side. Imagine learning astronomy by watching rings cross and tilt around a central Earth. The instrument did not bring the stars closer, but it brought their structure into human hands. It made the cosmos teachable. Ancient Indian texts described eclipse causes without relying only on myth. Myths about eclipses existed in many cultures, and India had famous stories involving celestial beings. Yet alongside myth, Indian astronomical texts developed physical explanations. Some traditions described eclipses as the result of shadows and alignments involving the sun, earth, and moon. This was a major intellectual step. It meant that a frightening darkening of the sky could be understood as part of a predictable arrangement. Astronomers still worked within religious and cultural worlds, but they also used calculation. They recognized that eclipses happened only when the moon was near particular points in its path. That understanding helped turn awe into analysis. What is compelling here is not a simple replacement of story by science. It is the coexistence of both. People could preserve sacred narratives while scholars worked out celestial mechanics. This reminds us that ancient astronomy was often layered. A single eclipse might be a ritual event for the public, a mathematical problem for specialists, and a wonder for everyone. The star Canopus helped ancient navigators in southern waters. Canopus is one of the brightest stars in the night sky, but it is not visible from far northern regions. For navigators traveling in southern seas, it could serve as a valuable guide. Its appearance signaled a different sky from the one seen in northern latitudes. Sailors moving toward the tropics or beyond could use such stars to judge direction and position. In the Indian Ocean and other southern routes, knowledge of bright stars mattered deeply. The sky changed with latitude, and trained observers learned to notice those changes. Canopus also gained importance in several ancient cultures because of its brilliance. A star that bright naturally drew attention. It could mark seasons, guide movement, and enter stories. The fascinating part is how geography affects astronomy. A star may be central to one culture and invisible to another. Canopus reminds us that the ancient sky was not the same everywhere. Each horizon revealed a different set of tools. Indigenous Australians preserved detailed sky knowledge through oral traditions. Across Australia, Aboriginal and Torres Strait Islander peoples developed rich astronomical knowledge over many thousands of years. This knowledge was often held in story, ceremony, song, and seasonal practice. It included the behavior of stars, the moon, the sun, and dark spaces in the Milky Way. Some traditions used sky patterns to time food gathering, animal behavior, or weather changes. Others connected celestial features with law and teaching. Because this knowledge was transmitted orally, it depended on careful memory and cultural continuity. That does not make it vague. Oral systems can preserve highly detailed information when they are embedded in daily life and responsibility. One famous example is the emu in the sky, a figure formed not from bright stars but from dark dust lanes in the Milky Way. Its changing position can connect with seasonal events. This kind of astronomy expands what we think observation means. Ancient sky knowledge was not only about bright points. It could also be about darkness. Some Aboriginal traditions may describe ancient changes in the sky. Oral traditions can sometimes preserve memories across astonishing lengths of time. In Australia, researchers have explored whether some stories may refer to past astronomical events, landscape changes, or shifts in the appearance of the sky. This must be handled carefully, because not every story should be forced into a scientific explanation. Still, some traditions appear to contain observations that align with real natural phenomena. Stories about variable stars, meteors, or changing celestial patterns have drawn serious interest. The possibility is fascinating. It suggests that communities may have watched the heavens closely enough to notice rare changes and pass them down through generations. Unlike a written tablet, an oral account lives through performance and teaching. It can carry knowledge while also carrying law, identity, and meaning. If some sky changes were remembered this way, then human astronomy is even older and more diverse than many people imagine. The past may not always be stored in libraries. Sometimes it survives in spoken memory. Chinese oracle bones include early records of eclipses and comets. Oracle bones are among the earliest surviving written records from ancient China. They were usually made from animal bones or turtle shells, then inscribed with questions before being heated for divination. The cracks were interpreted as answers, and the inscriptions sometimes recorded important concerns of the Shang royal court. Among these concerns were events in the sky. Some inscriptions appear to mention eclipses or comet-like phenomena, showing that celestial events had political and ritual importance very early in Chinese history. The bones are extraordinary because they bring together writing, kingship, divination, and observation. They do not read like modern scientific notes, but they preserve moments when the sky interrupted royal attention. A sudden darkening or strange light could become a question directed to ancestral powers. For historians, these marks are precious evidence of early sky awareness. They show that astronomy in China did not begin with later official records alone. Its roots reach into the earliest surviving Chinese writing. Ancient astronomers tracked Mars because its backward motion was mysterious. Mars can do something that seems deeply strange when watched against the stars. Most of the time it appears to drift in one direction, but at intervals it slows, stops, and moves backward before resuming its usual path. This is called retrograde motion. We now know it happens because Earth, moving on an inner orbit, overtakes Mars. To ancient observers, however, the effect was a puzzle. The planet did not behave like an ordinary star. It brightened, changed speed, and traced a loop that demanded explanation. Mars became one of the great problems for anyone trying to build a rational sky model. Its reddish color also made it culturally striking, often linking it with force or conflict in different traditions. But the motion itself was the scientific challenge. A careful watcher could see that something was happening that simple circular motion could not easily explain. A mystery of Mars helped push astronomy toward more complex mathematics. A wandering red light forced the human mind to work harder. The Babylonians named many constellations after animals and divine figures. To organize the heavens, Babylonian skywatchers used names that reflected their world of gods, creatures, and symbols. Constellations were not merely random star groups. They were meaningful patterns placed inside a religious and cultural landscape. Some represented animals, others were linked with deities or mythic beings. These names helped observers remember regions of the sky and communicate positions. They also reveal how deeply astronomy was woven into Mesopotamian thought. The sky was imagined as ordered and populated, not empty. Over time, some Babylonian constellation traditions influenced later Greek astronomy. This means that parts of the star map familiar today carry roots far older than many realize. Naming was a form of control and understanding. A region of scattered lights became a figure, and that figure became part of a shared celestial language. The stars did not change when they were named, but human access to them did. The night became readable because culture gave it shape. Greek models used circles because perfect motion seemed heavenly. For many Greek philosophers and astronomers, the heavens belonged to a realm of order. Circles seemed to represent perfection because they had no beginning or end, and moved with elegant symmetry. This belief shaped how celestial models were built. Even when planets appeared to wander in complicated ways, theorists tried to explain their paths through combinations of circular motions. The commitment to circles was not foolish. It reflected a deep assumption that nature should be intelligible through geometry. The problem was that the sky did not always behave simply. Planetary paths looked uneven from Earth. To preserve circular perfection, astronomers added layers of mathematical complexity. This tension became one of the most important stories in the history of science. A beautiful idea guided observation, but observation kept resisting simplicity. The Greeks were trying to make the heavens rational in the most elegant language they knew. Their circles were both a triumph of imagination and a limit that later astronomy had to overcome. Ancient observers noticed Mercury never strays far from the Sun. Mercury is difficult to observe because it stays close to the Sun in our sky. It appears briefly after sunset or before sunrise, never climbing high into the dark midnight heavens. Ancient skywatchers noticed this behavior. Unlike Mars or Jupiter, Mercury did not wander across the whole night. It remained tied to twilight. This made it elusive, quaked, and easy to miss. Its appearances changed rapidly, which gave it a reputation for speed in several traditions. The reason is that Mercury orbits closer to the Sun than Earth does. From our viewpoint, it swings from one side of the Sun to the other, always remaining near its glare. Ancient observers did not know the orbital mechanics in modern terms, but they recognized the pattern. That recognition required attention to difficult moments of visibility near the horizon. Mercury teaches a different kind of astronomy. Some discoveries come not from staring at the grand midnight sky, but from catching a small bright point during the fragile edge of dusk. The moon's phases gave early farmers a visible rhythm for time. For farmers, timing can be the difference between abundance and hunger. The moon offered a rhythm that was easy to follow, even without writing. A thin crescent after sunset, a bright full disk, and a fading late-night moon could all mark the passing of days. Many communities used these phases to organize tasks, gatherings, and seasonal expectations. The relationship between lunar phases and farming was not always scientifically exact in the way modern agriculture measures soil, rainfall, or temperature. Yet, as a shared time marker, the moon was incredibly useful. Everyone could see it. Everyone could speak about it. A farmer did not need a palace calendar to know that a certain number of nights had passed. The moon also shaped nighttime labor and travel because its brightness changed the landscape. A full moon could make movement easier. A dark moon could make the world feel closed. In this way, lunar time was not only counted, it was lived. Stone circles across Europe often connect architecture with seasonal astronomy. Across Europe, prehistoric stone circles and related monuments show repeated interest in the movements of the sun and moon. Not every stone ring was an observatory, and each site needs careful study. Still, many alignments suggest that builders paid close attention to horizon events. A standing stone could mark where the sun rose at a turning point in the year. A gap between stones could frame a particular direction. These structures required coordination, labor, and memory. Their builders were not simply arranging stones at random. They were shaping places where sky events could be noticed, repeated, and perhaps celebrated. What makes these monuments so compelling is their silence. They left no written explanation. We have stones, landscapes, burials, and alignments. From these, archaeologists try to reconstruct intention. The result is not always certain, but the pattern is powerful. The sky was important enough to be built into the ground. Ancient communities made architecture that could listen to the year. Egyptian decans divided the night sky into star groups. The decans were star groups used by ancient Egyptians to organize the night and the year. Each decan rose at a particular time, and their sequence helped divide darkness into measured portions. This system was especially important in religious and funerary contexts. Some tomb ceilings and coffin lids showed decan lists, making the sky part of the journey beyond life. The decans also helped build early forms of timekeeping. As one group appeared, then another, the night could be followed in stages. This was not the same as looking at a clock face. It required trained attention and knowledge of seasonal change. Over the year, different stars rose at different times, so the system had to be understood as a living cycle. The decans show how Egyptians turned the night into an ordered procession. Darkness was not empty. It was structured by the arrival of stars, each taking its place in the celestial schedule that linked time, ritual, and eternity. Ancient Greeks separated astronomy from astrology more slowly than we imagine. Today, astronomy and astrology are usually treated as completely different fields. In the ancient world, the boundary was much less clear. Careful observation of the heavens could serve practical prediction, philosophical inquiry, calendar making, and personal interpretation. A scholar might calculate planetary positions with real mathematical skill, then also believe those positions had meaning for human affairs. This can feel contradictory to modern readers, but it made sense in a world where the cosmos was often understood as connected and purposeful. The gradual separation came later, as astronomy developed stronger physical explanations, and astrology failed to meet scientific standards. Still, the early overlap mattered. Astrology gave many societies a reason to preserve planetary data, refine tables, and care about exact positions. That does not make its claims scientifically valid today, but it helps explain its historical role. Ancient Greek sky study was a mixed inheritance. It contained serious geometry, inherited belief, and an enduring question about whether the heavens influenced life below. The Aztecs watched the sun from carefully chosen horizon points. In the highlands of central Mexico, the sun's position along the horizon could help mark seasonal change. Aztec observers used the surrounding landscape, including mountains and built structures, to track where sunrise appeared through the year. This mattered because the calendar was central to agriculture, ritual, and state life. A horizon point could tell trained watchers that a ceremony was approaching or that a seasonal transition had arrived. In a city as organized as Tenochtitlan, timekeeping supported political authority as well as religious practice. The sun was not just a source of light. It stood at the center of a worldview that demanded order and renewal. Watching it required attention to the local landscape. The horizon became a measuring scale, and the city's sacred geography helped interpret the year. This form of astronomy feels immediate and grounded. It did not require portable instruments. It used the place itself, turning mountains and sightlines into a solar calendar. The caracol at Chichén Itzá may have tracked Venus. The caracol is a round tower at Chichén Itzá, whose name comes from a spiral staircase inside. Its unusual shape has long attracted attention because many Maya buildings are more rectangular and platform-based. Some researchers have argued that windows and sightlines in the structure connect with important positions of Venus. The interpretation remains debated because buildings can be complex and later damage can obscure original intentions. Even so, the possibility is fascinating. Chichén Itzá was a major center where astronomy, ritual, and rulership were closely connected. A tower designed to observe Venus would fit the planet's importance in Mesoamerican timekeeping. Imagine watchers using a built opening to mark when the brilliant planet reached a meaningful place on the horizon. The structure would make the sky event repeatable and public. Whether every proposed alignment is accepted or not, the caracol shows how architecture could participate in celestial attention. A building could become a frame for a planet. Ancient Chinese astronomers called comets broom stars. The name is wonderfully descriptive. A comet can look like a bright head with a sweeping tail, as though something has brushed light across the sky. Ancient Chinese astronomers used terms often translated as broom stars for these striking visitors. Their records frequently describe the length, direction, color, and location of the tail. This attention matters because comets change appearance as they approach the sun and then recede. To ancient courts, they were often interpreted as warnings or signs of disorder. Yet the descriptions were observationally valuable. A comet is not fixed like a star, and it may appear only briefly. Recording it required urgency and precision. The image of a broom also reveals how people made sense of unfamiliar phenomena through familiar objects. The sky presented something strange, and language reached for a household tool. That simple phrase still feels vivid. It captures both the shape of the object and the emotional shock of seeing a long-tailed light where none had been before. Babylonian eclipse warnings sometimes protected kings with substitute rulers. When Babylonian scholars predicted or identified a dangerous eclipse omen, the king could be considered at risk. In some cases, a substitute king ritual was performed. A temporary figure was placed on the throne while the real king withdrew from public danger. The idea was that the evil sign might fall upon the substitute instead. To modern ears, this sounds dramatic and unsettling, but it reveals the seriousness with which celestial omens were treated. The ritual also shows how astronomy could directly affect political action. A calculation or observation was not merely recorded. It could change the behavior of the court. Scholars held great responsibility because their reading of the sky might trigger costly rituals. This practice also reminds us that prediction did not always create comfort. Knowing an eclipse might come could intensify fear if the event was believed to carry divine judgment. In Mesopotamia, sky knowledge was powerful because it could protect authority, but also because it could threaten it. Ancient skywatchers could predict seasons by watching heliacal risings. A heliacal rising happens when a star becomes visible just before sunrise, after a period of being hidden in the sun's glare. This is a subtle but important event. It requires watching the eastern horizon at dawn and knowing which star has returned. Many ancient cultures used such risings as seasonal markers. Because stars reappeared at predictable times in the solar year, they could signal changes in weather, farming, sailing, or ritual life. The event is not dramatic like an eclipse. It is quiet, brief, and easy to miss without training. That makes it even more impressive as a tool. A community that followed heliacal risings had to maintain memory across years. The first glimpse of a returning star could mean that a familiar season was near. The heavens were not just measured at midnight. They were read in the pale edge before daylight. A tiny point of light, appearing at the right time, could tell people that the year had turned. Greek astronomers knew the moon shines by reflected sunlight. The moon looks luminous, but some Greek thinkers understood that it does not create its own light. It reflects the light of the sun. This insight helped explain lunar phases. As the moon moves around Earth, we see different portions of its sunlit half. The idea also helped make sense of eclipses and the changing geometry of the sun, Earth, and moon. Recognizing reflected light required careful reasoning. The moon's bright side always faces toward the sun in the sky. Its crescent shape changes in a pattern that matches its position relative to the sun. Once that connection is noticed, the moon becomes less mysterious and more astonishing. It is a world whose appearance is shaped by sunlight and perspective. This was a step toward treating celestial bodies as physical objects rather than pure signs or lamps. The moon became a sphere in space, half lit and half dark. Ancient observers were beginning to understand that what we see depends on where we stand. Theophrastus linked lunar halos with coming weather changes. A halo around the moon can appear when moonlight passes through ice crystals high in the atmosphere. To ancient observers, it was a striking sight, a pale ring surrounding the night's brightest body. Theophrastus, a student of Aristotle, wrote about weather signs and included observations connected with halos. People noticed that such rings could precede changes in weather, because the high clouds that create them may arrive ahead of storm systems. This was not astronomy in the narrow modern sense, but it belonged to a broader ancient study of the sky. The same observer who watched stars might also watch clouds, winds, and atmospheric light. Farmers and sailors cared deeply about these signs. A lunar halo could suggest that rain or unsettled weather was approaching. The importance lies in practical observation. Ancient science often began by asking what the sky was telling people about tomorrow. A glowing circle around the moon became a clue in the difficult art of forecasting nature. Ancient astronomers used gnomons to measure shadows and seasons. A gnomon is one of the simplest astronomical instruments. It can be as basic as an upright stick. Yet from its shadow, ancient observers could learn a great deal. At noon, the shadow changes length through the year as the sun's height changes. By tracking that shift, people could identify solstices and follow seasonal progress. A gnomon could also help determine direction, because the shortest shadow of the day points along a north-south line depending on location. The instrument's power lies in its simplicity. It turns sunlight into geometry on the ground. No moving parts are needed. No rare material is required. A careful observer can make the sun reveal time, direction, and seasonal change. In ancient cities and sanctuaries, larger gnomons could support more formal measurements. The shadow became a messenger. It stretched, shortened, and turned with dependable order. A plain vertical rod taught humans that the sky's great cycles could be read from Earth's surface. The Jantar-Mantar observatories continued ancient naked-eye astronomy traditions. Built in the early 18th century in India, the Jantar-Mantar observatories are later than many ancient sites, but they preserve an older tradition of naked-eye precision. Their huge masonry instruments were designed to measure celestial positions with remarkable accuracy. The best-known sites include Jaipur and Delhi. Instead of small handheld tools, these observatories used architecture itself as the instrument. Giant sundials, curved walls, and carefully shaped structures allowed observers to track time, altitude, and celestial coordinates. The scale is breathtaking. By making instruments large, builders reduced certain errors and made measurements easier to read. These observatories show that naked-eye astronomy did not simply vanish when telescopes appeared. In some traditions, it continued as a sophisticated craft. The Jantar-Mantar sites feel like stone mathematics. You can walk among angles and arcs built for the sky. They remind us that the human eye, when supported by careful design, remained a powerful astronomical tool for far longer than many imagine. Greek star catalogues helped reveal that stars slowly shift positions. A star catalogue is more than a list. It is a snapshot of the sky at a particular time. Greek astronomers who recorded star positions created a way for later observers to compare the heavens across generations. This mattered because the sky appears almost fixed during one human life. Yet careful comparison can reveal slow changes in the coordinate framework caused by the gradual motion of Earth's axis. Star catalogues also helped improve navigation, teaching, and astronomical models. They turned the sky into data. Each entry gave a star a measured place rather than only a mythic identity. The work required patience and discipline because naked-eye measurements were limited and difficult. Still, the act of cataloguing changed astronomy. It allowed the heavens to become something that could be checked against earlier observations. When later scholars saw differences, they could ask whether the stars had moved, the system had shifted, or the measurements had improved. A catalogue made the sky accountable to memory. Ancient people noticed tides were connected to the moon. Anyone living near a coast could see that the sea rose and fell, but linking that motion to the moon required careful attention. Ancient observers noticed that tides often followed lunar timing. The connection was especially important for sailors, fishers, and coastal communities. In some places, tides shaped when boats could enter harbors or when shellfish could be gathered. Greek and Roman writers discussed the relationship, although they did not have the modern gravitational explanation. They understood that the moon and the ocean were somehow connected. That idea is beautiful because it joins the sky with the movement of water at one's feet. A body far above Earth seemed to reach into the sea. Today, we explain tides through gravity and the motion of the Earth-Moon system. Ancient people did not need that full theory to recognize the pattern. They saw that the moon kept time with the shore. The ocean became another way. The heavens made themselves known. The zodiac began as a practical path for tracking planets. Before the zodiac became famous in popular astrology, it served a more basic purpose. It marked the belt of sky through which the sun, moon, and planets appeared to travel. Ancient astronomers needed a way to describe positions along that path. Dividing it into named sections made observation and prediction easier. If Mars appeared in one region and Jupiter in another, the report could be understood by other scholars. The zodiac was therefore a celestial roadway. Its signs helped organize movement against the background stars. Over time, this practical framework gained symbolic meanings, but its observational usefulness came first. The planets do not roam randomly across the whole sky. Because the solar system is relatively flat, they stay near the same broad track. Ancient skywatchers recognized this and turned it into a map. The zodiac's endurance comes partly from that practical foundation. It gave humans a way to follow wandering lights with shared language, night after night, century after century. Ancient sky maps often mixed careful observation with sacred storytelling. A sky map can be accurate and meaningful at the same time. Ancient people often recorded star patterns while also connecting them to gods, animals, ancestors, or heroic events. This was not necessarily a failure of observation. It was a way of making the sky memorable and important. A cluster of stars could guide seasonal work while also carrying a story that taught identity or values. The map and the myth supported each other. In cultures without mass-printed diagrams, storytelling helped preserve celestial knowledge. Names and narratives made patterns easier to teach. They also gave the heavens emotional weight. Modern star charts usually strip the sky down to coordinates and labels, but ancient maps often kept the human meaning visible. This blend can feel surprising to us because we separate science and story more sharply. Yet the stars were never just data to the people who watched them. They were part of a living world of memory, order, and wonder. The Chinese guest star of 1054 created the Crab Nebula. In the summer of 1054, court astronomers in China noticed a brilliant new light in the sky. It was so bright that it could be seen during the day for several weeks. At night, it remained visible for many months before fading from sight. To the observers who recorded it, this was a guest star, a temporary visitor that had appeared where no familiar star belonged. Today, we know they were seeing the explosion of a massive star. At the place they described, modern telescopes reveal the Crab Nebula, a glowing cloud of expanding gas with a rapidly spinning neutron star at its center. The ancient report gives that nebula a human timestamp. It tells us when the explosion reached Earth's skies. That connection is breathtaking. A careful note made in an imperial record now helps scientists understand the aftermath of stellar death. The light vanished from human eyes, but the wreckage still shines. Babylonian astronomers predicted Jupiter's motion with advanced mathematical schemes. Jupiter moves slowly compared with the inner planets, but its path is still complicated when seen from Earth. Babylonian scholars learned to handle that motion with numerical methods of surprising sophistication. Instead of building a physical model of the planet's orbit, they used tables that tracked changes in speed across time. Some surviving tablets show step-like calculations that allowed them to predict where Jupiter would appear. One method even resembles a form of geometric reasoning because it uses the area under a changing speed pattern to estimate distance traveled along the zodiac. This is astonishing because it shows that abstract mathematics could emerge from sky watching. They were not merely writing down where a bright planet appeared. They were transforming repeated observation into calculation. Jupiter became a problem that numbers could solve. The result is one of the great achievements of ancient astronomy. In a world without telescopes, scholars learned to forecast the motion of a giant planet through disciplined arithmetic. Babylonian skywatchers tracked Venus so carefully that kings feared its omens. In ancient Mesopotamia, Venus was not just a bright point near dawn or dusk. It was a celestial sign watched with intense attention. Babylonian scholars recorded its first appearances, disappearances, and returns with extraordinary patience. They knew it moved in a repeating rhythm, and they treated each change as meaningful. These observations were written on clay tablets, then preserved in libraries and temple archives. To the royal court, the planet's behavior could suggest danger, victory, famine, or divine favor. A strange appearance might lead to rituals meant to protect the king. This may sound superstitious now, but the observation behind it was serious. The Babylonians were building a record of the sky across time. Their belief system gave urgency to their science. Because rulers cared deeply about these signs, astronomers had strong reasons to watch carefully. In that way, fear and curiosity worked together. The result was one of the earliest long-term planetary records in human history. Maya astronomers calculated Venus cycles with remarkable long-term accuracy. For the Maya, Venus was one of the most important objects in the sky. Its appearances were tracked with care because the planet moved through a striking pattern. It appeared as an evening star, vanished into the sun's glare, returned as a morning star, and disappeared again. Over time, Maya astronomers understood that this cycle repeated after 584 days. They also noticed how several Venus cycles could be matched against their calendar system. The result appears in the Dresden Codex, one of the few surviving Maya books. Its Venus table allowed priests to anticipate appearances over long periods and adjust for small errors. This was not casual stargazing. It required arithmetic, tradition, and a deep commitment to watching the same planet across generations. What makes it so compelling is the mixture of precision and meaning. Venus was a measured body in the sky, but it was also woven into ritual timing and political decisions. The planet became both a clock and a warning. Greek thinkers imagined celestial spheres carrying stars around Earth. To explain the daily turning of the heavens, many Greek philosophers pictured the cosmos as a set of nested spheres. Earth rested at the center, while the stars and planets were attached to transparent shells moving around it. The idea may sound strange today, but it was a serious attempt to make sense of a sky that appeared orderly and circular. Each sphere could rotate with its own motion, producing the observed paths of celestial bodies. This system also gave the universe a beautiful architecture. The stars were not scattered at random. They belonged to a structured, layered cosmos. Later, thinkers developed more complicated versions, adding spheres to explain planetary irregularities. The model was wrong in its physical arrangement, yet it reveals something important about ancient science. People were trying to imagine hidden machinery behind visible motion. The turning sky seemed to demand support, order, and cause. Celestial spheres were an elegant answer before gravity changed the question. Ancient Egyptians watched circumpolar stars that never seemed to set. Near the northern part of the sky, some stars circle around the pole without dipping below the horizon. To Egyptian observers, these stars were deeply meaningful because they appeared deathless. While other stars rose and vanished, the circumpolar stars remained in endless motion above the north. They became associated with permanence and royal afterlife beliefs. In pyramid texts, the dead king could join these imperishable stars and share their eternal presence. This was astronomy woven into the most intimate hopes of a civilization. The sky offered a visible image of survival beyond decay. It also shaped architecture and ritual. Passageways and sacred orientations may have reflected attention to the northern heavens. What makes this so powerful is the simplicity of the observation. A person watches night after night and notices that certain stars never disappear. From that fact grows an idea of immortality. The heavens did not merely measure time for Egypt. They offered a model of forever. The Karnak temple complex includes alignments linked to solar events. Karnak was one of the greatest religious centers of ancient Egypt, and its architecture developed over many centuries. Among its courts, pylons, and sanctuaries are alignments that connect the built environment with the sun's movement. In particular, parts of the complex relate to sunrise around significant points in the year. When sunlight enters along a planned axis, architecture becomes more than stone. It becomes an event that can be repeated by the heavens. Such alignments helped reinforce the relationship between temple ritual and cosmic order. Priests did not worship in a space cut off from nature. They worked inside a structure designed to receive light at meaningful moments. The effect would have been dramatic for those who knew when to watch. A beam of sunlight could move through sacred space as if confirming that the temple belonged to the order of the world. Karnak shows how astronomy could be embedded in ceremony, not as decoration, but as part of divine timing. Ancient Romans inherited much of their astronomy from Greek sources. Roman sky knowledge was shaped by conquest, translation, education, and admiration. As Rome absorbed Greek culture, it also absorbed Greek astronomy. Educated Romans studied Greek texts, used Greek constellation names, and repeated Greek explanations of celestial motion. They were often more practical than theoretical, applying astronomy to calendars, agriculture, timekeeping, and public life. The Roman calendar itself went through major reform under Julius Caesar, influenced by astronomical knowledge from the Eastern Mediterranean. This inheritance mattered because Rome became a powerful carrier of older ideas. Through Roman writers, Greek astronomy reached later European traditions. Some Romans loved the sky as a subject of philosophy. Others treated it as useful knowledge for navigation or farming. The result was not a simple copy. It was a transfer into a new cultural world. Astronomy moved with language, empire, books, and schools. The heavens stayed the same above the Mediterranean, but their explanations traveled through Roman hands into the future. The Seleucid Babylonians recorded planetary positions with impressive consistency. During the Seleucid period, Babylonian astronomical diaries became especially detailed and regular. Scholars recorded where planets appeared, along with lunar events, weather notes, river levels, prices, and other observations. This combination may seem surprising, but it shows how sky watching belonged within a wider habit of monitoring the world. The planetary entries were often precise enough to reveal long-term patterns. Because they were written consistently, they provided a foundation for better predictions. A single observation can be interesting. A long series becomes powerful. The Seleucid records show a professional tradition working night after night, year after year. These scholars were heirs to much older Mesopotamian practices, but they pushed numerical astronomy to remarkable levels. Their work helped transform omen-based watching into systematic prediction. The clay tablets are modest objects, yet they preserve a disciplined encounter with the planets. They show that ancient astronomy could be patient, bureaucratic, mathematical, and quietly brilliant all at once. Ancient astronomers separated fixed stars from moving planets by patient watching. At first glance, the night sky can look like a single field of lights. But careful observers learn that not all lights behave alike. Most stars keep the same arrangements relative to one another. They form patterns that return with the seasons. A smaller group shifts position against that background. These moving lights became known as planets. Recognizing the difference required repeated observation across many nights. It also required memory. A bright object that seemed ordinary one week might have moved noticeably by the next. That discovery changed the structure of the sky. The heavens were no longer one uniform dome. They contained a stable background and a set of wanderers crossing it. This distinction became essential for calendars, prediction, mythology, and later physical astronomy. It is easy to overlook how profound this first sorting was. Before anyone could explain planetary motion, someone had to notice that a few stars were not staying with the others. Patience revealed a hidden order. The moon's nodes explained why eclipses do not happen monthly. If the moon passes around Earth every month, it might seem that eclipses should happen just as often. Ancient astronomers eventually understood that the moon's path is tilted relative to the sun's apparent path. Because of this tilt, the moon usually passes above or below the perfect line needed for an eclipse. The crossing points of these two paths are called nodes. Eclipses can happen only when the moon is near one of them at the right phase. This insight was crucial because it explained a mystery that simple lunar cycles could not solve. New moons happen often, but solar eclipses are rare. Full moons happen often, but lunar eclipses do not come every month. The nodes made the pattern understandable. They turned eclipse prediction from guesswork into geometry. Ancient astronomers did not need modern orbital diagrams to grasp the importance of these crossing points. By learning where the paths met, they learned why darkness sometimes arrived and why it usually did not. Early Chinese star maps divided the heavens into lunar mansions. Chinese astronomy organized the sky in a way that differed from the familiar Western constellation tradition. One important system divided the path of the moon into 28 lunar mansions. These were sections of sky used to track the moon's nightly progress and to organize celestial positions. Each mansion had its own name and associations. The system provided a practical framework for observation, calendar work, and interpretation. Because the moon moves quickly against the stars, a mansion-based map made its changing position easier to describe. This was a different way of thinking about the heavens. Instead of focusing mainly on large mythic figures, it emphasized a sequence along the moon's road. Star maps and manuscripts later preserved these divisions with remarkable detail. The system reminds us that there is no single natural way to map the sky. Cultures build celestial order around the questions they ask. For Chinese astronomers, the moon's path became a backbone for reading the heavens. Ancient Indian nakshatras tracked the moon's nightly path among stars. The nakshatra system divided the sky along the route traveled by the moon. Each nakshatra marked a region associated with particular stars, allowing observers to describe where the moon was on a given night. This system became deeply important in Indian astronomy, calendrical practice, and ritual timing. Because the moon changes position noticeably from night to night, the nakshatras offered a clear celestial sequence. They also helped connect sky observation with cultural life. A ceremony, birth, or festival could be related to the moon's place among these star fields. The system is fascinating because it treats the moon as a traveler moving through a series of stations. Each night it visits a new part of the heavens. This gives time a living rhythm, visible to anyone trained to recognize the pattern. The nakshatras show how astronomy can organize both calculation and meaning. They made the moon's journey readable, giving ancient observers a way to follow time across the stars. The Greeks calculated Earth's tilt with careful solar measurements. Earth's axis is tilted, which is why the sun's height changes through the year and seasons occur. Ancient Greek astronomers did not know Earth's motion in the modern sense, but they could measure the angle between the celestial equator and the sun's yearly path. This angle is what we now call the obliquity of the ecliptic. By using instruments and observing the sun's noon height at different times of year, they estimated the tilt with impressive accuracy. The measurement required patience because the difference between solstice extremes had to be tracked carefully. It also required geometry. The changing sun was not merely felt as warmth or cold. It became an angle that could be calculated. This is one of the great achievements of naked-eye astronomy. The seasons were translated into mathematics. Ancient observers learned that the year's changing light followed a measurable rule. In doing so, they turned everyday experience into a precise statement about the structure of the sky. Ancient farmers used star risings to time harvests and migrations. For many farming communities, the return of certain stars carried practical meaning. A star appearing at dawn or rising in the evening could signal that crops were nearing readiness, animals were moving, or weather was shifting. These observations were local and specific. A pattern useful in one region might not apply in another. That is what makes them so human. Ancient astronomy was often tuned to particular landscapes, soils, rains, and food sources. Farmers did not study the sky only from curiosity. They watched because their lives depended on timing. The stars offered a seasonal memory that could be shared across generations. Before printed almanacs, a familiar rising could announce that work should begin. This knowledge blended observation with tradition. A parent might teach a child which star mattered, when to look for it, and what it meant for the fields. In this way, astronomy entered the rhythm of labor. The sky helped people know when the Earth was ready. The temple of Abu Simbel was aligned with rare sunrise events. At Abu Simbel, the great rock-cut temple of Ramesses II creates one of ancient Egypt's most famous light effects. On specific days of the year, sunlight reaches deep into the sanctuary and illuminates statues inside. The event is often associated with dates near the king's birthday and coronation, although details are debated. What matters is the intention. The builders carved a monument into the rock so that the sun would enter at rare moments and animate the sacred interior. This required a sophisticated understanding of direction, horizon, architecture, and the solar year. The effect would have reinforced royal power and divine connection. A viewer could see the sun itself honoring the innermost space of the temple. Later, when the monument was moved to save it from flooding after the Aswan High Dam project, engineers worked to preserve the solar phenomenon as closely as possible. Abu Simbel shows how ancient astronomy could become theater in stone, staged by the rising sun. Early astronomers studied eclipses because they revealed cosmic geometry. An eclipse is not only dramatic, it is a rare alignment that exposes the arrangement of celestial bodies. When the sun or moon darkens, observers are seeing shadows and positions made visible on a grand scale. This made eclipses valuable to early astronomers. They could reveal that the moon crosses the sun's path only under special circumstances. They could show that Earth casts a curved shadow. They could help estimate sizes, distances, and alignments. For ancient thinkers, an eclipse turned the invisible structure of the heavens into an event. It was like a lesson written across the sky. Fear may have surrounded these moments, but curiosity followed closely behind. A person who asked why the darkness came had to think in terms of bodies, paths, and light. That is cosmic geometry. Eclipses helped move astronomy from wonder toward explanation. They showed that even the most startling sky events belonged to order. The darkness was temporary, but the insight could last for centuries. The planet Saturn marked the slowest visible wanderer in ancient skies. Among the planets known to ancient observers, Saturn moved with the greatest slowness. Night after night, it shifted only gradually against the stars. Over months and years, its progress became clear, but it demanded patience. Because of this measured pace, Saturn often gained associations with age, time, and distance in later traditions. To the naked eye, it appears as a steady yellowish point. Its rings were invisible before telescopes, so ancient astronomers knew it only as a remote wanderer near the limit of ordinary sight. Its long cycle made it useful for marking extended periods. Unlike Mercury or Venus, which remain close to the Sun, Saturn could cross the night sky in a stately rhythm. Watching it taught observers that not all planets moved alike. Some darted, some blazed. Saturn seemed to endure. It was the farthest known planet in many ancient systems, standing near the edge of the visible planetary family. Its slow motion made the universe feel larger. Ancient records of comets helped establish their repeated returns later. For much of history, comets seemed unpredictable. They appeared suddenly, grew tails, and disappeared into darkness. Ancient observers often treated them as unique events. Yet the records they left became crucial for later astronomy. When scholars began to calculate cometary paths, they could compare new appearances with older descriptions. Dates, positions, brightness, and tail direction helped identify whether a comet had been seen before. This was especially important for establishing that some comets return on long orbits around the Sun. The realization changed their nature completely. They were not one-time warnings or atmospheric disturbances. They were members of the solar system, traveling on vast paths through space. Ancient records made that discovery possible because they gave later astronomers a long memory. A comet that returned after decades or centuries could be recognized only if someone had written down its earlier visit. The sky's strange visitors became predictable partly because ancient witnesses preserved their arrivals. The Maya tracked Mars as well as Venus and eclipses. Although Venus often receives the most attention in discussions of Maya astronomy, Mars also mattered. Its motion is slower and more complex than Venus in some ways, especially because it can brighten dramatically and show retrograde movement. Maya sky specialists observed planetary cycles within their broader calendar systems. Evidence suggests they paid attention to Mars's intervals and incorporated them into astronomical tables or related calculations. This shows that their interest in the heavens was not limited to one brilliant planet. They were watching a larger planetary order. Mars would have stood out because of its reddish color and changing brightness. Its behavior required long-term attention, since its cycle relative to Earth is longer than a year. Tracking it meant thinking across extended periods and fitting observations into a sophisticated calendar culture. The Maya approach reminds us that ancient astronomy could be wide-ranging and ambitious. It did not stop at the most obvious lights. It followed difficult wanderers too. Greek astronomers debated whether the universe had a central fire. Not every Greek thinker placed Earth at the center in the same way. The Pythagorean philosopher Philolaus proposed a strange and daring model in which Earth moved around the central fire. This fire was not the Sun as we understand it. It was a hidden cosmic center, with Earth and other bodies circling it. The idea may seem odd now, but it matters because it broke from the assumption that Earth must sit motionless at the middle of everything. It shows that ancient Greek cosmology was more varied than a simple geocentric story. Philosophers were experimenting with deep questions. What belongs at the center? Is Earth special? Could our world move? Some answers were wrong, but the willingness to ask was revolutionary. The central fire model did not become the dominant scientific tradition, yet it hinted at a powerful possibility. The ground beneath human feet might not be the fixed heart of the cosmos. That thought would return with force much later. Ancient cultures often connected the Milky Way with roads or rivers. The Milky Way stretches across dark skies as a pale band of light. Without modern knowledge of galaxies, ancient people still saw that it was different from ordinary star patterns. Many cultures imagined it as a path, river, smoke trail, or bridge. These interpretations were grounded in its appearance. It arches across the sky like a root. It glows softly like a celestial current. Such images helped people place the feature into familiar experience. In some traditions, it was a road for souls. In others, it was connected with animals, water, or creation stories. Today, we know it is the crowded disk of our own galaxy seen from within. That scientific truth is magnificent, but the older interpretations are also revealing. They show how humans responded to a striking natural feature before its physical nature was known. The Milky Way invited explanation because it was too obvious to ignore. It made the sky feel inhabited by direction, movement, and destination. The Dunhuang Star Atlas preserved thousands of stars on paper. Discovered among manuscripts from a cave library near Dunhuang in China, this star atlas is one of the great treasures of astronomical history. It dates to the early medieval period, but it preserves traditions rooted in much older Chinese sky mapping. The atlas shows thousands of stars arranged across multiple charts, with constellations drawn and labeled according to Chinese systems. Its survival is extraordinary. Paper is vulnerable to fire, moisture, insects, and time. Yet this document endured in the dry conditions of the cave. For historians, it reveals how carefully the heavens were mapped before the age of telescopes. It also shows a different celestial order from the one many modern viewers know. The star groups are not the Greek mythic constellations. They belong to Chinese court astronomy and its own organized vision of the sky. The atlas turns fragile paper into a preserved night. Looking at it, we see the heavens as scholars charted them more than 1,000 years ago. Ancient Chinese astronomers recognized lunar mansions across the moon's path. The moon moves quickly, shifting its position among the stars from one night to the next. Chinese astronomers used lunar mansions to follow that motion with structure and clarity. These mansions formed a sequence along the moon's route, giving observers a way to describe where it was and how it progressed. The system also supported calendar making, omen interpretation, and official sky reporting. Each mansion carried names and associations that belonged to Chinese cosmology. This made the moon's journey both measurable and meaningful. The idea is elegant because it treats the sky as a set of stations. The moon does not wander through an unmarked field. It passes through recognized regions, night after night. This allowed astronomers to communicate observations with precision. It also helped create continuity between generations of records. When a court observer named a mansion, later readers could understand the location. The moon's changing place became part of a shared celestial language. The Greeks used epicycles to explain strange planetary loops. When planets appear to reverse direction against the stars, a simple circle around Earth does not explain what the eye sees. Greek astronomers answered this problem with epicycles. In this model, a planet moved on a small circle whose center moved along a larger circle. By combining these motions, they could reproduce loops, changes in speed, and shifts in brightness more successfully than a single circle could. The system became especially important in later geocentric astronomy. To modern readers, epicycles can seem like an awkward patch. Yet they were mathematically clever. They allowed astronomers to preserve circular motion while matching real observations more closely. This was a serious attempt to find order beneath complexity. The planets seemed to dance in puzzling ways, and epicycles gave that dance a pattern. Even though the physical model was eventually replaced, the mathematical ambition behind it mattered. It showed that astronomy would not accept appearances passively. It would build machinery of thought to explain them. Ancient observers saw meteor showers as rare and meaningful sky events. A meteor streaking across the sky can startle even a modern observer. For ancient people, repeated bursts of such lights must have felt especially powerful. Meteor showers occur when Earth passes through trails of debris left by comets or asteroids, but that explanation was unknown. What people saw was a sudden increase in falling stars. Some cultures treated them as omens, messages, or signs of change. Others folded them into stories about spirits, weapons, or celestial fire. Because meteor showers are seasonal, attentive observers could notice that certain displays returned around the same time of year. The challenge was that they were brief and depended on clear, dark skies. A person had to be watching at the right hour. That made the experience feel rare, even when the pattern repeated. Ancient meteor watching reminds us that not all astronomy was slow and predictable. Sometimes the sky erupted in motion. A dark night could suddenly fill with sparks, and people remembered. The sun's noon height helped ancient people find latitude. Latitude is a way of knowing how far north or south you are, and the sun can help reveal it. At noon, when the sun reaches its highest point, its height above the horizon changes depending on location and season. Ancient observers who understood this could compare solar altitude with expected values. This was especially useful for travelers, geographers, and astronomers. A simple shadow measurement could become a clue to position on Earth. The method required corrections for the time of year because the sun's path changes seasonally. Still, the principle was powerful. The sky offered a way to locate oneself on a curved planet. In the ancient world, where maps were limited and travel could be uncertain, that knowledge mattered. It connected astronomy with geography. The same sun that warmed fields and marked days also helped define place. By measuring its height, people could turn the heavens into a coordinate system for Earth itself. Ptolemy's Almagest preserved earlier Greek astronomy in extraordinary detail. The Almagest became one of the most important scientific works ever written because it gathered, organized, and extended centuries of astronomical knowledge. Ptolemy drew on earlier Greek traditions, including observations and models from figures such as Hipparchus. He presented star catalogues, mathematical techniques, and planetary theories in a systematic form. The work was so comprehensive that it became the standard reference for astronomers across many cultures. Later, scholars translated, studied, corrected, and debated it. Its influence reached the Islamic world and medieval Europe, shaping astronomy for generations. The book's importance does not depend on its geocentric framework being ultimately correct. Its value lies in its mathematical detail and preservation of earlier work that might otherwise have been lost. Through it, ancient observations traveled far beyond their original time. The Almagest is like a library compressed into one monumental text. It shows that scientific history is not only about discoveries, it is also about transmission, survival, and the careful organization of knowledge. ancient skywatchers could estimate time at night by star positions. Before mechanical clocks were common, the night could still be measured. Stars rise, cross the sky, and set in predictable patterns. A trained observer could use their positions to estimate the hour. This skill mattered for guards, priests, travelers, and anyone whose duties continued after sunset. Different stars were useful at different seasons, so the method required both memory and experience. It was not enough to know one constellation. The whole turning sky had to become familiar. In some cultures, special star lists or diagrams helped people divide the night into watches. The principle is simple but profound. Earth's rotation makes the heavens appear to move, and that motion can serve as a clock. Imagine standing outside in darkness, without a bell tower or wristwatch, and knowing the time because a certain star had reached a certain place. The night was not timeless. It had structure, and ancient skywatchers learned to read it. Some ancient monuments reveal lunar alignments as well as solar ones. Solar alignments are often easier to notice because the sun's annual extremes are dramatic and regular. Lunar alignments can be more subtle. The moon's rising and setting points shift through a longer cycle, reaching major extremes only after many years. Some ancient monuments appear to reflect awareness of these lunar standstills. This suggests that builders watched the moon across extended periods, not merely from month to month. Such alignments are difficult to prove, and each site must be studied carefully. But where the evidence is strong, it reveals a remarkable level of attention. The moon was not only a phase-changing light, it also had horizon patterns that could be tracked over years. Building those patterns into stone would have required patience across generations. A monument with lunar alignment is therefore a record of long observation. It shows a community looking beyond the obvious solar year and noticing a slower rhythm in the night sky. Astronomy helped ancient rulers claim order, power, and divine approval. In many ancient societies, rulers gained authority by presenting themselves as guardians of cosmic order. Astronomy supported that claim. A king who controlled the calendar could schedule festivals, taxes, labor, and rituals. A ruler whose priests predicted sky events could appear connected to hidden knowledge. Monuments aligned with celestial events could make political power feel woven into the structure of the universe. This was not only propaganda. It reflected a worldview in which heaven and society were linked. If the sky moved in order, the kingdom should also move in order. When celestial events seemed unusual, they could be interpreted as warnings that rulers had responsibilities to correct. This gave astronomers and priests influence at court. Their knowledge helped shape public time and royal legitimacy. The heavens became a mirror in which power was displayed and judged. Ancient astronomy was therefore never only about stars. It could help organize states and strengthen the people who ruled them. Ancient astronomy began with naked eyes and changed how humans understood reality. The first astronomers had no lenses, rockets, cameras, or computers. They had eyesight, memory, patience, and the shared knowledge of their communities. With those tools, they discovered cycles in the sky, built calendars, guided journeys, organized ceremonies, and asked questions that still matter. They learned that appearances can hide deeper patterns. A planet can seem to wander, but follow a rule. A shadow can reveal the shape of Earth. A star can mark a season. These insights slowly changed humanity's sense of place. The sky was no longer just a ceiling above the world. It became a system that could be studied. This is the lasting wonder of ancient astronomy. It began with people looking up from fields, deserts, coasts, temples, and cities. It grew into mathematics, architecture, navigation, and philosophy. Every modern observatory inherits something from those first watchers. They proved that careful attention could turn wonder into knowledge, and knowledge into a new vision of reality. And so our journey through ancient astronomy comes gently to a close. Tonight, we followed the first skywatchers as they looked upward with nothing but their eyes, their patience, and their desire to understand. We saw how the moon became a measure of time, how the sun shaped seasons, and how the stars helped people find their way through darkness. We visited temples, towers, stone circles, desert monuments, and ocean routes. Each one reminded us that the sky was never far from daily life. Across the ancient world, people watched the heavens with care. They learned that eclipses could be anticipated. They noticed that planets had strange wandering paths. They turned shadows into measurements, stars into calendars, and sunrise into ceremony. Even without telescopes, they found patterns fast enough to guide kingdoms, harvests, voyages, and belief. There is something calming in that thought. Above every generation, the same sky kept turning. Above every sleeping city, every riverbank, and every quiet field, the stars moved with patient rhythm. People came and went. Languages changed. Kingdoms rose and faded. But the heavens remained, offering light, direction, and mystery. So now, as the facts settle softly in your mind, let the old sky drift farther away. Let the constellations blur into stillness. Let the moon hang quietly above the edge of sleep. There is nothing more you need to follow now. Nothing more you need to remember. If you enjoyed this gentle journey, you're welcome to like, subscribe, or leave a thought below. It helps others find their way here too. And if you happen to still be awake, another calm exploration should be waiting on the screen for you. But for now, let your shoulders soften. Let your breathing slow. Let the night become simple again. Sleep well, and good night.